Lecture. All right, so last time we introduced the concept of one-way versus two-way floor systems and also defined tributary area and looked at tributary width as well. So today we're going to continue with that and actually start applying it to some examples. So just a real quick recap, right? Your handout starts with this page. We've got a couple of one-way span examples shown here, and these are all plan views, right? So looking down on the floor. And then on the next page, you've got the two-way span. And we'll come back to this maybe today if we have time, but my plan is to come back to this if we have time for some more in-depth discussions. But just briefly here, right, you can tell by looking at the layouts of these what direction the floor surface will span, right? So for these one-way spans, and in your book, it talks about learning to understand and read these floor plans and understand the load path, and they refer to a load path hierarchy or vertical load path hierarchy. And so this is kind of what I'm touching on here. So of course the floor surface is the first thing, right? That supports the loads that are on it. And then that surface transfers those loads to whatever is directly supporting it. Oftentimes it's a set of beams, right? It could be walls, or in the case of a two-way floor system, it could just be columns. But in this case, we're looking at one-way spans, so we can see these beams, all right, that are oriented like that, those are what directly supports the floor. And the way we can tell this just by looking at the floor plan, there are a couple of clues. One, you can see that there are some gaps at the ends of these beams where they hit the girder lines, right? So that's an indicator that those beams are supported by the ones that don't have the gaps there. And then also the fact that the girder lines are a little more bold, that indicates, that that's a beam that supports other beams, or, it's further down in the hierarchy of the load path. So because these first level of beams are spanning left to right on the page, we can conclude that the floor span, or the span of the surface, is perpendicular to those beams, right? And so the hierarchy would be the surface to the cross beam, and then they would go to these secondary girders, all right? Now technically, these girders on the outside would be primary girders, right? Because they're supported by columns. But as far as the hierarchy of the load path is concerned, they're at the same level as these secondary girders, okay? Because they directly support those cross beams. So then that first level of girders would then either be directly supported by the columns in the case of the perimeter ones, or by other girders in the case of the beams. All right, so some of those girders go directly to the columns. And then in the example below, right, we can identify these beams as the ones that directly support the floor surface based on the cues noted above. Another cue is that, they're shorter, there are more of them, right? And the spacing between them is smaller, okay? So those are all clues that those beams directly support the floor surface. And so we can say that the floor spans in the direction perpendicular to those beams. Questions? Yes?
When looking at structural plans, is it typical that they leave out the floor surface and they just put the structural members on the plan?
Yeah, for structural floor plan layouts, that is common. A lot of times then there will be details that show what the floor surface is, or it'll be taken care of in notes, because usually it's, not always, but usually it's the same everywhere, right? So yeah, I'll see if I can find an example to show you of a project that I worked on that has a floor layout. Yeah, I'll try to bring that in. I'll make a note of that and try to bring that in next week to show you guys. Because I think that is good stuff to get exposed to and to see. All right, so then on the next page, right, you have the two-way span where your floor surface is directly supported by columns. And all right, you can say that floor will span in two orthogonal directions. And in reality, right, if it's a reinforced concrete slab, then in reality it can kind of distribute the load in multiple different directions. It depends on how it's reinforced. But a lot of times, right, cracks will occur, or the load distribution might look something like that in reality. And this is also then how we would divide up tributary areas. So kind of following those lines. All right, or I should say that would be the more accurate tributary area, the actual one. But in our practice, we would simplify it, all right, to lines that are drawn halfway to the next supporting column for those columns. So we'll look at that a little bit more later too. All right, and then we looked at these examples of different surfaces. So now we're going to kind of dive more into this concept of tributary area and how to apply it. So we talked about this last time, right? We can use tributary area and tributary width to condense our loads to whatever it is that is relevant to the element that we're analyzing. So we can use tributary width to condense a line load to a point load. Or to condense a surface load to a line load. And then we can use tributary area to condense a surface load to a point load. All right, so let's first consider this flat plate supported by columns. Would this be a one-way or a two-way floor system? Good, yeah, two-way floor system. And since we are in a two-way floor system, then we will just use tributary area to condense the surface load to the point loads on the columns. So because columns are considered point elements with respect to vertical loads, right? They're just located at discrete locations. We want to know what point load acts on it. So to find the point load on the column, all right, we would start by acknowledging that this lowercase p shown down here in the formula represents the pressure load or surface load that's acting over the area. And the units are typically in pounds per square foot, which we often just note as PSF. So then that just gets multiplied by the tributary area for a given column, right? And then we know the point load on that column. So I always like to do gut checks on units when you run calcs, right? PSF times square feet gives us pounds, which checks out. So pretty straightforward there. And again, this is a regular layout floor plan, right? In this class, I'm not going to get too crazy with tributary areas for you guys, so just going to try and keep it simple. In practice, we would usually use AutoCAD or something to calculate tributary areas, especially if the floor layouts were irregular. All right, so now if we consider this flat plate supported by beams, would this be a one-way or a two-way floor system? One way, right? So the floor system, the floor slab would transfer the forces to these beams that directly support it, and then those beams would transfer the forces to the columns. So one clue that it's a one-way floor system is due to the fact that, see the difference in the spans. So the distance between the beams is a lot smaller than the distance between any supporting element in that direction, right? And in your book, I think it gives you a ratio. So generally speaking, in practice, there's sort of a rule of thumb that is used to kind of gauge whether a floor system is one-way or two-way, and that's if the width to length of the area between supporting elements is above or below 2, I think is the cutoff that they use. So you can use that as an indicator, but there are other things that you have to think about as well. For example, think about that load hierarchy, right? The load path hierarchy. A floor plate can only transfer forces to an element that directly supports it. So we'll look at an example in the next page where you do have beams in both directions, but only one of those directions directly supports the floor, right? So you have to think about that because that will tell you if that's the case, then it has to be a one-way floor system, right? Also, if you have if you have a floor surface that's something like this, right, where you've got the corrugated metal decking that can really only transfer load in one direction, then it has to be a one-way floor system, regardless of what that ratio is, all right? So use that ratio with a grain of salt. It's not always going to give you the answer. All right, so this is a one-way floor system, and since we are looking at the beams that are directly supporting the floor plate, we want to, what type of load are we looking for on these beams, right? So previously we condensed a surface load to a point load to the columns. Well, what about beams? What would you expect to see the load? A line load, right? Yeah, since beams are line elements, if they directly support the floor surface, we would expect to see a line load on those beams from that floor. So we'll say find the line load on beams directly supporting the floor. And that's shown by this equation here, all right? So we just take the pounds per square foot times tributary width gives us a line load in pounds per foot. And here, all right, I've noted what the tributary width is of each beam. So if you were to calc that, that would be for beam AD, that would just be equal to half of this distance D1 noted over here. And then CF would have a tributary width equal to half of D2. And then the beam in the center would have a tributary width equal to half of the sum of those two distances. Okay. Questions? Yeah.
If there were a column directly in the center of the middle beam, would it be a two-way system?
No. So that's a good question. So you're asking if there was a column here.
Yeah.
So if that was the case, all that would really be doing in this layout, if we didn't make any other adjustments, it would shorten the span of these beams, right? So these two beams would have shorter lengths, and then they wouldn't need to be as deep, those two beams, right? But it would still be a one-way floor system.
You'd have
Yeah.
to have beams going to the left and right of that one as well, or up and down.
So if there's a lot of different things that would need to change in order to turn this into a two-way floor system. Yeah, if you had kind of a regular, network of beams in both directions like that, then it could be designed as a two-way floor system, right? If you had a concrete slab in between and you reinforced it in both directions, you could do it that way. But again, it depends on what that floor surface is, how that surface can transfer forces itself, and then whether those beams in both directions are directly supporting the floor slab. So you could arrange for that to happen. Yeah. But just based on this configuration, it should be pretty evident that it's a one-way floor system. So, yeah. All right, so now we've kind of thought through this qualitatively. I've got a few more comments on things related to floor systems that can also give you clues as to whether it's a one-way or a two-way. And then we'll roll into an example with numbers. All right, so most beam girder systems are constructed in a manner that causes them to be what we call flush. And that means that the elevation of the top of the girder is at the same level as the elevation of the top of the beam that frames into it, right? So in this situation, both the girder and the beam will directly support the floor plate, but that doesn't necessarily mean that it's a two-way floor system, right? It just means that that girder will take on a little bit of that width of that floor surface area. However, we often will simplify it for our tributary area determination and use an approximate tributary area. And also when you have this scenario, right, depending on the geometry of the girder, you might need to make adjustments to the top of the beam that frames into it. So in this example, the top flange is cut away from this cross beam, and we call that coping. Of course, if it's just a rectangular cross section, you don't have to do that, but this allows that the web of that to reach in and attach to the girder there. So this is an example of what the actual tributary area divisions would look like for a flush system, right? So if these would be the girders, right, supporting beams in this direction. So those girders would technically take on some of that floor surface load. And then the actual loading on the girder would look something like this, right? So you've got point loads where the beams are framing into it at those locations, and then the distributed loads that follow the pattern of the tributary area designation, right? And the beam loading would be trapezoidal. So, of course, right, that's a lot more complicated to analyze than what we get out of the simplified or approximate tributary area, which is why even when we have this scenario, we would use the approximate tributary area instead, okay? Now, if we have a drop girder system, then the cross beams are supported by girders that are below the beam. And in that case, right, it wouldn't just be sitting on there. You'd have some bolts that are firmly attaching those two pieces. But in that case, there's no question, right? The girder does not directly support the floor slab. And so in this case, what we called approximate for this scenario, right, this tributary area, which I didn't sketch out, but right, the approximate tributary area would be something like that, right? In that case, it would be the exact tributary area. Yeah, questions? Okay. All right, so now we will look at an example. So I'm going to skip this page for a second and then we'll come back to it because I want to show you the example. So here we have a floor, right, floor plate that is directly supported by 3 beams spanning in this direction, okay? So we can see that by the way it's drawn. And then those beams are directly supported by 2 girders, right, like that. And then those girders are directly supported by the columns. So the hierarchy in this load path would be floor slab to the beams in this direction, to the beams in that direction, and then to the columns. All right. I'll have a few other comments on this page when we get back to it. But now that we've established that, we're ready to go, and I'm just going to kind of step through what I recommend you think through at the very least. You don't have to write this process out when you go through load path analysis, but I highly recommend that when you approach a problem, you think through it so that you know what to expect at each level, right? So this is kind of just breaking down the hierarchy. So the first step would be to identify the load that's applied to the element, or identify the applied load, excuse me, and the element directly supporting it. So in this case, that would be whatever load is given, or it would be loads that you determine through load specification. Since we haven't covered load specification in this class yet, loads are given for now. So in the example, all right, it's a surface load that's given. And also in this example, right, we have identifying the element directly supporting it. So that's just saying, okay, the floor plate directly supports the surface load. All right, so then the next step would be to identify the members that directly support the element that you identified in the previous step, right? So those are those 3 beams that I highlighted yellow on the other page. They were labeled A, B, C, D, and E, F. And those support the floor surface continuously. All right, so because it's a continuous support, we would expect to see a line load. right? And we would get that by taking the surface load multiplied by the tributary width of the beam. So I'll label this as the beam. And that beam would be supported at each end by a girder. And I'll say this is equal to surface load times the tributary width. All right, and then you continue with this process, right, until you reach the foundation. So the next level would be the girders AE and BF. And also note that those girders support the beams at discrete points. All right, so we would not expect to see a distributed line load on those girders. We would expect to see point loads. And I think, yeah, the configuration was evenly spaced, so we would have 3-point loads. And those girders are supported at each end by columns. Now here, all right, these point loads are coming from the reactions that we found in the previous level, right? So these are the same thing. I'll say equal magnitude. And here's our girder. All right, and then so on. You have the column supported by the foundation. And that's the same force, right? The reaction that you found from the girder would be then flipped around and applied to the column. Questions? Okay. So again, you don't need to write this all out and do all those sketches, except, you know, this is often part of the problem anyway, so you'll end up doing sketches like that, but the qualitative initial analysis, just think through it in your head. So back to this example then, we have a uniform pressure of 100 psf over the surface area, and then we are given the sizes of each beam, all right? So the cross beams that directly support the floor are W6 by 25s, and the girders are W10 by 60. So if you're not familiar with the W designation, it stands for wide flange, the W does, and it's your typical I-beam shape, right? The first letter, or the first number in the designation, represents the approximate depth in inches. All right, so I'll note here. And then the second number in the designation represents the self-weight of the beam in pounds per linear foot. So we're going to use that information, and we will include the self-weights of these beams in our load path analysis. And we're asked to find the load path of the forces through this structure. So when you're asked to find the load path, that means that you need to report the correct loading on each member, right, and show it on free body diagrams. And that includes the correct magnitude, direction, distribution, and units. I'll write that out. And when I say each member, typically one representative, right, because there's a lot of repetition, one representative of a given level in the hierarchy is sufficient. All right, questions? Far so good. All right, so the first analysis that we'll do will be on that first level of beams. All right, so we'll consider the edge beams first. All right, so looking at beams A, B, and E, F, these two beams support all of the surface load that's halfway to the center the center beam. Okay, so your tributary width of each beam is going to be 2.5 feet. Do better. All right, so all the load that falls in that zone will go to that beam and similarly over here. And since those two beams are the same, we only need to do this analysis once. Right? It can represent both beams. So we know we're going to end up with a line load. And that's going to be equal to the surface load, which was given as 100 pounds per square foot, times the tributary width of 2.5 feet. So 250 pounds per foot. Now that's what we call the superimposed loading, right? Because it's load from outside of the beam itself. Now we need to include the self-weight of the beam to get the total load. So we're going to add to that um, 250 plus 25 pounds per foot. All right, so we're in pounds per foot. Gives us 275 pounds per foot is the total line load on that beam. And then from statics, we can find the reactions pretty readily. I'm not going to go through the whole statics calculation, but I'll write the results. And because this beam is simply supported and just has a uniform line load on it, the formula is simplified to WL/2 for those reactions. So let's say, just write the final result, 1375. All right. So the length is equal to 10 feet. All right, so now similarly for the center beam, now we just have a larger tributary width. All right. So now our tributary width is 5 feet. We expect a line load. And so we take 100 times 5 gives us 500. And then we add to that 25. So we get a total load of 525 pounds per feet. And that includes our self-weight, right? So notice that we didn't just take the load on the edge beams and double it, right? Why not?
Because the width is different.
The width is different, but the width is twice, right? So tributary width here is double the tributary width here. So why don't we just take this load and double it?
Because the self-weight doesn't double.
Right, yeah, we don't want to double the self-weight, right? So I'm just pointing that out because it's a common mistake that's often made. And it's tempting, I get it. All right, and then once again from statics, we'd get reactions of 2625 pounds upward from statics. All right, so now we've done that level within the load path hierarchy. On to the next level, which would be the girders. Since the two girders are essentially the same, right? They have the same tributary width and the same beams that they're supporting, just on two different ends. We can sketch the anticipated loading. And I'm going to do this in this example, but you do not have to do this in your work. You do not have to show the self-weight as a uniform load. So actually, I'm not going to do it because I don't want you to feel it. I don't want you to think that you have to do it. But you do need to note, all right, that the self-weight is included. So we'll say self-weight. The girders were 10 by 60, so self-weight is 60 pounds per foot. All right. So then the only loading that we need to draw on the diagram would be that superimposed loading. So that's going to be 1375 at the two ends. Don't forget the units. And then at the center, 2625 pounds. And then you can use statics again to find the reactions at A and E. And then the forces on the columns would be the reactions that you found. We'll use RA as a representative. All right, just applied in the downward direction at the top of the column. So then technically, if we were going to continue this and figure out what the load is that's transferred into the foundation, at each column, it would be RA plus whatever the self-weight of the column is, right? Which we weren't given in this example, so we won't go through that. Okay, questions? Yes?
And you calculated it in this order because of the hierarchy?
Yeah, so you always want to follow the hierarchy, yeah. And you can check, so, one way to check your work could be to, going back to the floor plate, you can see that the columns, right, have a tributary area of 10 times 10, so, or 5 times 5, right? So 25 square feet is the tributary area for the column. So you could do a check and take the 100 PSF times 25. That would give you the superimposed load from the surface, and then you could factor in the self-weight, the portions of the self-weights from the beams. It can get a little bit tricky though because, right, you've got this center beam, so how much of this center beam is going to each column, right? So you just have to think about all of those things, but that is one way you can, arrive at the answer a different way or check your work, right? Yeah. Any other questions? Okay. So of course your homework problem is going to be a little bit more involved and a little bit more complicated than this example, but the steps are the same, right? Go through the same process, draw the free body diagrams, make sure you include the loading in its correct magnitude, distribution, direction, and units, right? And then I've got another example here for you. This I'm going to treat as a practice problem, so the solution should already be on D2L, but I'll verify that for you under the examples and practice problems folders. So this is just thinking about the load path in a vertical fashion, right? So you've got a wind load applied to a billboard, and this billboard is supported at 5 locations, all right, by trusses that are identical to the one shown. So down here is looking down in plan at the locations of those 5 trusses, all right? So the load would be attacking the billboard like that. But the billboard is only in the top 16 feet of those trusses, right? So you've got that 30 PSF over the top 16 feet and then 60 feet in length, right? So calculating what that force is going to be transferred then to a typical interior truss. So looking at a truss that has, right, an interior tributary width. So what will those point loads be at those locations? So this is kind of set up to guide you through that process, and then I'll provide the solution on D2L, right? So that's a good practice problem for you for load path. And then in the few minutes that we have remaining, I will go back to this page as promised. So I want you to think about, we'll look at this floor plan here because it's a little more complicated than the other one. You have one more level in the load hierarchy than this one, right? This one, you really only have 3 levels, or 4, I guess, right? You have the floor surface, and then the cross beams, and then the girders, and then the columns. Here you have like 2 levels of girders to deal with. So think about one of these, let's see, go ahead and label the cross beams, right? So I'll color code it. So one of those interior cross beams would have a tributary area, something like that, right? And then every single one of those cross beams, right, its tributary area, altogether, they would have to cover the entire floor plate. And then if you go to the next level, right, these guys, all of their tributary areas would also have to encompass the entire floor plate, and so on for each level, okay? So if you mix the levels tributary areas will overlap, and that's okay, right? Because your column tributary area would be something like this. For this inside girder, your tributary area would be like that. They overlap, but that's because they're at different levels within the hierarchy. So if they're within the same level, the tributary areas should not overlap. So with that in mind, and everything else that we've talked about, why don't you think about a crossbeam and then one of these interior girders has a tributary area like that. And just sketch what the load application would look like on each of those beams. So what would the free body diagram of a crossbeam look like, and what would a free body diagram of the interior girder look like? And then if you get that done, do the next girder. So one of these guys. Has a tributary area that covers half the floor plate, right? Not really, though. That's very conservative. So that one would technically be more like that. All right, so for the cross beam, right, it should just look something like this, a line load, and then supports at each end, right, simply supported beam. And if we call these, right, R1, and since it's simply supported and with a line load on it, those reactions on both ends will be the same. What did you get for this girder?
Like 3-point loads.
Yeah, 3-point loads. Right. And what would be the magnitudes of those point loads?
R1.
Yeah, the reaction. So R1. So if R1 is here and here and here and here and here and here, what would be the magnitude of the point load right here on this beam?
2R1.
Yeah, 2R1. Yeah, so you have to think about that too. The interior beams support two sides of cross beams, right? So you would have supports on those beams and then point loads of 2R1 for interior, right? But these edge ones would just have 1R1. And then the next level of girders, right, would be supported by the columns and just have 2 point loads with magnitude of R2. Right. Okay. All right. Any questions? Good deal. All right, well, have a great long weekend. I'll see you on Wednesday. And yeah.